So in my last video we looked at what a gas was in terms of those 5 assumptions. Remember those? They were that there's many molecules in rapid random motion, that the volume of those molecules is negligible compared to the volume of the container, that the force they feel is nothing except when they collide, that those collisions that take place are perfectly elastic, all of the kinetic energy is conserved, and that the time it takes to collide is negligible compared to the time between collisions. Those 5 assumptions are crucial and critical, and don't think that I'm going to stop saying them in order like that. They're really, really important. Today we're going to look at what a gas does. We're going to think about how we can measure a gas. And it's fairly straightforward. I was trying to experiment with these. Unfortunately, Sainsbury's was out of balloons, and so I'm going to have to use sandwich bags here. A gas has a volume. Inside this bag is a volume of gas. But that volume can change. If I squeeze it, I can change both the shape and the volume of that gas. But I can feel it pushing back against me. And that's because in trying to reduce the volume, you're increasing the pressure that that gas will exert on you. Pressure and volume are inversely proportional. P is inversely proportional to V. So if you're going to plot pressure on the y-axis of a graph, and volume on the x-axis, it will be a classic 1/, curve like that. Not very useful if we want to analyse it. If we want to analyse it, we have to plot a pressure against 1/, volume graph. The gradient of that would be the constant of proportionality in this case. Obviously, in a question, if you're given a pressure and a volume, you can then just use that to try and work out what the constant of proportionality is and then what the final answer will be. You know how proportionality works. I'm not going to lecture you with it here. The second relationship is to do with temperature. If you think about it, like everything, like every substance, the volume that a gas occupies increases with temperature. They expand. Everything expands with temperature. Gas is no exception. So it comes pretty simply that temperature and volume are directly proportional. Temperature and volume are directly proportional. If it's hotter, it takes up more space. Again, we can do a graph, and you might think, oh, this is easier. Stop. This is not a straight line through the origin. At 0 degrees Celsius, I can walk outside and breathe perfectly normally. In fact, in Canada, in Siberia, we see regularly temperatures of like -22, -50. At 0 degrees Celsius, a gas still has a volume. The graph of temperature on the x-axis, volume on the y-axis, it's a straight line, positive gradient, but it has a non-zero intercept. That is essential. Get it straight in your mind. Temperature, volume starts from non-zero. Otherwise, we'd all suffocate on a frosty day. I'm going to ask a quick question. What happens if I trace that line back? If I keep going into the negative, where is the point that reaches 0? You're right. We can't have a negative volume, and in an ideal gas, where there's no forces between the particles, that means that it has no potential energy either. So the internal energy of a gas is all kinetic. If I cool a gas down, its kinetic energy reduces. So what happens when it reaches 0 and I can't take out any more kinetic energy? There's a point where all of the molecules in a gas will stand still. They will have no energy whatsoever. I can't extract energy from a system that has no energy. There is an absolute minimum temperature that we can have at -273.15 degrees Celsius. That absolute minimum temperature is 0 on the Kelvin temperature scale. We're going to just call it 0 Kelvin, the absolute minimum temperature that can occur. You cannot have a temperature of less than 0 Kelvin. You cannot have one. By all means, go and try and prove me wrong. I welcome the news when you're in your 40s as a professor of physics. It will be fantastic for science, but also it will never happen. 0 Kelvin is the lowest temperature that you can have. Temperature actually is one of those things which has an absolute zero and it will just keep increasing. If 0 Kelvin is minus 273 degrees Celsius, then what would 0 degrees Celsius be in Kelvin? The answer is it would be 273 Kelvin. And that leads to a dead simple conversion. The temperature in Kelvin is the temperature in degrees Celsius plus 273.15. Simple. The temperature in Kelvin is the temperature in degrees Celsius plus 273.15. So room temperature is 20 degrees Celsius, generally. What would that be in Kelvin? It would be 293 Kelvin. Minus 73 degrees Celsius would be 200 Kelvin. We don't say degrees Kelvin, that just sounds silly. We just say Kelvin. Why am I talking about Kelvin here? Well, it's really important because if we're going to use volume being directly proportional to temperature, in order for that to work properly, for the volume to be 0 when the temperature is 0, to get that proper graph, which is a straight line through the origin, the temperature has to be in Kelvin. It does not work for temperatures in degrees Celsius. So the biggest new thing from the last 2 videos is this fact. Kelvin is the absolute temperature scale with a 0. And to find out what a temperature is in Kelvin, you take the temperature in degrees Celsius and add 273 degrees. Doesn't mean that you don't have to learn those 5 ideal gas assumptions. Pressure and volume are inversely proportional. It doesn't mean that you don't have to learn how gases exert pressure on the wall, or that the change of momentum is 2mv. It doesn't mean that you don't have to learn about those graphs. You have to learn all of those things. But do some practice. Whenever you see a temperature for the next few days, convert it into Kelvin. Because Kelvin is the most logical temperature scale. Starts at 0 and it just keeps going up. What I would like you to do is just do a quick bit of practice learning those ideas. There's an assessment coming up as well, so spend some of this additional time that you've gained getting ready for that assessment. I'll see you later in the week where we'll talk about moles and the ideal gas equation, and then we'll round it all off with energy in our gas.